have calculated the spacing by first criteria, that is, first thing is spacing is equal to what we have calculated. It is 160 mm center to center. This is our spacing. Okay, we have provided 16 mm diameter bar and we have calculated the spacing in the last lecture. How to calculate the spacing? Now you know that. What is the formula to calculate the spacing? The spacing can be calculated as area of one bar divided by total AST into width. Here B is 1000. AST provided we always take while calculating the spacing. Okay, so now after this calculation, now we will see the second thing, spacing. So spacing is equal to, as per the IS code, we should calculate the spacing by 3 into D, that is 3 into effective depth of the west slab. Now what is the effective depth we have calculated? It is 3 into 280 is our overall depth. Now what is our effective depth? Calculate the effective depth. 280 minus cover minus kara 20 mm, 15 mm, 15 mm cover. Then initially we have assumed 10 mm bar diameter, now it is 16, so you can calculate the effective depth. It is 230. Okay, so it is 3 into 230. What is the answer? So I will show you where it is given first. So we will move to the IS code. Okay, so if we move to the IS code, here you will notice that this is given over here. So in the IS code, the reinforcement, if you read this clause, then what they have told you, the horizontal distance between parallel main reinforcement bars shall not be more than 3 times the effective depth. So I underline the word here, it is 3 times the effective depth. Okay, so 3 times the effective depth, it is already given. So that we are using. And the second clause, what it says, what the second clause, so not in the second clause, and the sentences continue with that, 300 mm whichever is smaller. Okay, so for the spacing, now the next clause is 3 times the effective depth and 300 mm whichever is smaller, that we need to calculate. Okay, so now we will go back to our problem. Now here 3 into D, so how much it is? 3 into D, 3 into D, how much it is? 3 3s are 9, 2 3s are 6, 609 mm center to center. Okay, and third is spacing. In no case the spacing is 300 mm center to center. Now choose the value which is minimum out of these three. We are going to choose the lesser value of these three. So the lesser value is 160. Okay, so here I will write, so here I will write provide 16 mm diameter bars about 160 mm center to center. Okay, about 160 mm center to center. Now these are our main steel bars. Okay, so these are our main steel bars. Now we will provide distribution steel. The staircase slab is always designed as a one-way slab. Staircase slab is always designed as a one-way slab. So in one-way slab, in shorter direction normally we provide main steel, and in another direction we provide distribution steel. In the same way, in the staircase, for this we have provided now the main steel bars, that is the main reinforcement. Now we are going to provide the distribution steel. So I will write the second heading, distribution steel. Distribution steel. So now to provide the distribution steel, what we are going to do here, we know the clause for the distribution steel. Okay, if mild steel is there, then it is 0.15% of the total gross area, and if it is torch steel is there, Fe415 or Fe500, then it is 0.12% of gross area. So that you have already studied in DCS-I. So many times we have referred this from the IS code. Okay, so now I am taking it directly. So the distribution steel is 0.12% of gross area. Okay, so ASTD, distribution steel, is equal to 0.12%, so it is 0.12 divided by 100 into, what is the meaning of gross area? It is B into D. Okay, so width is 1000, you know that, and overall depth is also known to you. So moving further, ASTD is equal to, it is 0.12 divided by 100 multiplied by 1000 multiplied by 280. What is the answer? If you solve this, you will get the answer. Let me know the answer fast. 336. Okay, so the answer is 336 mm square. As it is area, we will take it in mm square. Okay, so now we will choose one diameter on this side also. Okay, so we will choose 8 mm diameter bars, as this area is very less, 336 mm square. So provide 8 mm diameter bars. So we will provide 8 mm diameter bars, and let us see now what is the spacing of this. So we will calculate the spacing now. Okay, spacing of bars. So we will calculate the spacing of these bars now. First thing, spacing is equal to, how do we calculate the spacing? So it is here area of single bar. Okay, so area of single bar divided by ASTD, distribution steel. Here we need the value of provided, what we have provided. Okay, ASTD provided into width. Width is 1000. So for this now we need distribution steel provided. What distribution? ASD provided. So we will calculate the value of ASD provided now. So here ASD provided, to calculate the ASD provided, first we need to calculate the number of bars. Okay, so first we will calculate number of bars. The number of bars is equal to total area, that is 336, divided by area of single bar. Area of single bar. So let me know the answer. 336 divided by area of single bar divided by area of single bar. What is the answer? It is 6.68. Okay, so the answer is 6.68. So we will round up this to 7 numbers. Okay, so 7 bars are required. So now calculate ASTD provided. Now what is the ASTD provided? So here now ASTD provided is equal to, how many bars we have provided? 7 bars into diameter of single bar is 8, pi by 4 into 8 square. Now you will get the answer. Solve this and let me know the answer. Answer is 351.86. Okay, so it is 351.86 mm square. Now this is provided ASTD. Now we will move back to our spacing. So spacing of bars we were calculating over here in the last slide. If you see here, this is the spacing of bar which we are calculating. Here put the value of ASTD. Okay, put the value of ASTD. So what you will get, area of single bar, that is pi by 4 into 8 square divided by this value 351.86 multiplied by 1000, as our width is 1000. So let me know the answer. 142.85. Okay, so here it is 142.85 mm. So we will round this up to on the lesser side, that is 140 mm center to center. This is our spacing. Now there are two more clauses for the spacing given by the IS code. Spacing of distribution steel. Spacing. Okay, and what should be the spacing? Now you already know that what are those two clauses. So many times we have studied, but still we will go to the IS code now. Okay, so here now see the IS code. I will underline it. The second point, the horizontal distance between the parallel reinforcement bars provide against the shrinkage and temperature. So this is nothing but shrinkage steel, minimum steel, okay, minimum steel and distribution steel. These are the same, only the names are different. हे एकाचेच नाव आहेत सगळे. डिस्ट्रीब्युशन स्टील म्हणजे पण तेच, मिनिमम स्टील इज ऑल्सो डिस्ट्रीब्युशन स्टील, श्रिंकेज स्टील इज ऑल्सो डिस्ट्रीब्युशन स्टील and temperature steel is also distribution steel. Okay, so now what they have further told us, shall not be more than 5 times. Okay, it shall not be more than, here if you see, 5 times the effective depth, 5 times the effective depth, or 450 mm, or 450 mm, whichever is smaller. So now again we will move to the our whiteboard. So now coming back to the whiteboard, what is the spacing now? So it is 5D, so it must be equal to 5 into 230. So let me know the answer. And last one is 450 mm. So calculate this one, 1150. Okay, so 1150 mm center to center, it is 1150. Okay, so this is the these are the three spacings which we got now. So we will choose the minimum value. So I will write here, provide 8 mm diameter bar about, what is the minimum spacing? It is 140 mm center to center. Okay, instead of 8, if you provide 10 mm bar diameter, then spacing will get increased. Okay, so this is the distribution steel. Now after providing the distribution steel, we will calculate the development length of the bar. Okay, what is the development length. So as you know that for development length, the formula is LD is equal to phi sigma s upon 4 tau BD, which is equal to, what is the diameter of our main reinforcement? You should take the diameter of main reinforcement phi. From where this formula originate? This is from our IS code. Okay, if you forgot, then we will move to the IS code to rebrush it. So the formula is given somewhere here on page number 42, I think so. Okay, here is the formula. Now you can see the formula. What is the formula? LD is equal to phi sigma s upon 4 tau BD. What the each term says, phi is the nominal diameter of the bar. This is the phi. Then sigma s is the stress in bar section considered at the design load. Means what? So sigma s is nothing but sigma s is equal to 0.87 Fy. Okay, and then tau BD is the design bond stress given in this table 26.2.1. Okay, so if you go to this table 26.2.1, you will get the bond stress. Okay, so now here is the table 26.2.1, and here in this table, see for M20, it is 1.2. For M20 it is 1.2, and again this is very important information which is given over here. Okay, if you see, for deformed bars conforming to IS 1783, these values shall be increased by 60%. Okay, and for the bars in compression, the value of the bond stress bars in tension shall be increased by 25%. Okay, if the bars are in compression, it is further increased by 27%. Okay, so when it is in tension, we need to multiply this value, or we need to increase this by 60%. Means what? We are increasing it by 16%, means we need to multiply this by 1.6. This is nothing but increase by 60%, and for this 25% we need to multiply by 1.25. so this is the increase by how much? 25%, further increase. Okay, so now we will go back to our problem again. So now here I will write the values so that it will you calculate it fast. So phi is 16 into 0.87 into sigma s is 415, okay, whole divided by 4 into tau bd value is 1.2, and we use deformed bars, so it is 1.6. You should multiply it by 1.6. So from this you will get the value of development length. So calculate the development length now. Calculate it now and let me know the answer. Okay, 752. So the answer is 752.18. Okay, so it is 752.18 mm. So development length, it is in, we can increase this, so it is 755 mm. This is the development length what we have calculated. Now we will draw the reinforcement details. Okay, so to draw the reinforcement details now, I will try to draw the staircase. You also draw this drawing now. Okay. So now this is the landing here. This side also. You draw the need diagram so that you will understand. This is our approach, or this is also landing. I will join this. Now see how the main reinforcement is placed. Main steel bars. Okay. So the main steel bar, I will start it from here, then up to this point, and then it will move parallel here from the bottom. Okay. So I need to draw it by free hand. I will draw it. So from this point now, there is a bent up like this up to this point here. Okay. And from here onwards, it will move straight. We will draw it again. It bent like this, and after that it will move straight up to this point. Okay. Now further, this bar is continued. Further, it is continued here up to this point, and after that, finally, it goes up. So this is your main steel bar. Okay. So this is your main steel bar, and it is about what it is. You know that 16 diameter bar. For this bar is now, if we give the name, so this bar, it is 16 diameter, about 160 center to center. Okay, this is the bar, and the distribution steel is, if I show over here the distribution steel, then the distribution steel is also provided. Before showing the distribution steel, I will show the bent up bars here in this. So the bent up bars are provided here. Now the bar will be like this. Up to the development length, these bars are provided. Okay. So this will move further somewhere here. Okay. And now from this point, it bends and it will move like this. Okay, this is the bar which is provided for the development length. Similar kind of bar is provided at this point also, here at the first landing, and that bar I will draw now. You draw the reinforcement details with me. So now here the second bar is like this only. Okay, and from here it will move up to the development length. And now we need to show the distribution steel. So distribution steel is provided like this. Here is the distribution steel. These bars, whatever I am showing over here, these are the distribution steel. We have already designed this. Okay, all these bars are nothing but distribution bars. You also draw the diagram with me. And now I will give name to these bars. So these two bars are, what is the diameter? 8 mm diameter. 8 mm diameter. About what was the spacing of the distribution steel? 8 mm diameter bars. About what was the spacing? It is 140 mm. About 140 mm center to center. Now these remaining bars. Now if you think about these bars which we have provided over here, these two bars. Okay. These bars are the alternate bars which we have provided to resist the excessive bending moment, and these bars are having half of the area of this your main reinforcement. So these bars which we have provided over here in green, what we can say, the green shape, those are greening, those are having half of the area than this main reinforcement, that is this red steel. Okay, so now if you see half area means what? We need to increase the spacing, double the spacing, means area get reduced by half. So these are the 16 mm diameter bars. About, if this spacing is 160 main steel spacing, then this will be 320 mm center to center. Okay, and now the development length is also there. So this length, I will draw the arrow over here. So whatever this length is there, this total length, okay, this is nothing but your development length for this point also. Okay, and this length is works out to be, it is LD is equal to, we have calculated this length, and this length is 755 mm. This is 755 mm. Okay, 755 mm. So now I hope it is clear to you. Okay, so this is the design of staircase. In this way we need to design the staircase. I hope it is clear. If the diagram is over, let me know, then we will move to the next point. Diagram draw करून झाली असेल तर मला सांगा. So we will move to the next numerical then. Let me know in the chat if it is over. We will move further then. Draw the neat diagram. This is very easy easy design. And until you give me the reply, how can we move further? Is it over now? Have you finished this? Okay. So now moving to the next point. So now if you see here, these are some points you should from this point today we have start from distribution steel. We have calculated the area of distribution steel, then distribution steel provided, we have calculated the spacing of those bars. Again, you know the formula for spacing. Spacing is works out to be 140 mm for 8 mm diameter bar, and this is the last diagram, that is your reinforcement diagram. Now here, so now moving further, okay, so here now we will take the next example. So I will write the example, you write it down also, and then we will solve it. Again, there is maybe the change in the support condition in the numerical design. Design a dog-legged staircase. Design a dog-legged staircase of public building public building in a room so space is given again, measuring 2.8 by 5.8 meter. Clear measurement is given. Out the vertical distance between the floor is 3.6 meter. Full stop. Width of flight is to be 1.25 meter. Allow a live load of 3 kilonewton per meter square. Assume the stairs are supported. Assume the stairs are supported. The stairs are supported as shown in figure. Not assume here. The stairs are supported as shown in figure. That is the sentence only. The stairs are supported as shown in figure. Okay. Now assume M20 concrete and Fe415 steel. So these are the given things. Now the given diagram is there. Okay, so I will draw the staircase. So here it is the rectangle. This is the staircase now total. Here is the landing. Here also some landing part is there. Then you copy this diagram with me, and now support is provided over here. See, like this the support is provided. This is the plan, and in this way it is supported now. Okay. So these are the supports. Here this is the support. So now the slab is not spanning in the direction of the stairs. Okay, slab is not spanning in the direction of the stairs. So this type of support is given over here. This is your landing, and in between the steps are given here. This is your going length. Okay, so total length is what they have told to us, that it is 2.8 by 5.8. Again the things will, we will calculate how much is this going length and what the width is remaining for the landing. Now these are the support. So this is 230 mm wall. Okay, I will write here. What is this? This is wall, which is having a thickness of 230 mm. Okay, so this type of support it is given over here. So step by step we will develop this diagram. Now the thing is that we need to do our basic calculations. First of all, we need to find out the number of risers, number of treads, and effective span, and all the things. Okay, so now how many number of risers and number of treads, how we are going to find out? We need to fix the riser, then tread, what are the dimensions. Okay, so first of all we will use 150 mm riser. Okay, consider riser is equal to 150 mm, which is 0.15 meter. Okay, so now floor to floor height. What is floor to floor height? Floor to floor height, it is given as 3.6 meter, which is equal to 3600 mm. Okay, so number of risers now. Number of risers. How do we calculate number of risers? It is 3600 divided by it is 150, single riser. So if you solve this, you will get the number of risers. So how many number of risers? 3600 divided by 150. Do the calculation and let me know the answer. 24. आता आपण टोटल ह्याच्यातले रायझर्स काढले बरं का, 24 numbers. In last problem we did half of this, half of 3600. In last problem we did half of 3600 and then we divided by riser and we get the number of risers in single flight. Now here if you divide it and do it by the same way, that is also correct. If you first of all calculate the total number of risers and then divide it by 2, so you will get the number of risers in a single flight. Okay, so number of risers in single flight, that we will calculate. So number of risers in single flight, so it is 24 divided by 2, which is 12 numbers. Are you getting the point? Okay, In the previous numerical, we have done it by different way. In the previous numerical, what we have done, we had divide this 3600 by 2. If you pay attention over here carefully, we divide this 3600 by 2. Half floor to floor height means what? A single flight is there, then landing is there, and then another flight is there. I have drawn the diagram at that time also. So that way also you will get the same answer. I will also show you by that way. Okay. So now floor to floor height is 3600. So height of single flight. Okay, this is the alternative. Alternative. By this way also you can calculate the same. The height of single flight. What is the height of single flight? It is 3600 divided by 2. This is the height of single flight. So 1800 mm is the height of single flight. Okay. Now we will calculate the number of risers in single flight. So number of risers in single flight. So it will be 1800 divided by, what is our riser? Riser is 150. So if you do 1800 divided by 150, I think it is 12. Calculate it. You will get the answer 12. So 12 is your answer. So I have shown you both the approaches. Okay. I have shown you both the approaches. So in the last numerical, we have done by this way, whatever I have shown in the green ink, that we are done in the last example. And now we have calculated the number of risers by this way, which is shown in the red ink. Okay, both of these is same. So whatever you find it as easy, you can adopt it. Hmm? So now next thing is that after the calculation of riser, we will calculate now number of trades. So number of trades, we are going to calculate number of trades. So number of trades, how do we calculate now? So number of trades T is equal to, what is the formula? It is R minus 1, number of risers minus 1. Okay, so number of risers are 12 minus 1, so it will be 11 numbers. So number of trades are 11. So now assume the trade dimension. Okay, so we will assume the trade, assume trade T is equal to, so we will assume something for a trade, and we will assume it as, again take it as 280 mm trade. Okay, so now we have assumed 280 mm a single trade, and how many trades are there? 11 numbers. Number of required trades are 11 in a single flight. Okay, in a single flight the number of risers are 12. So in a single flight number of trades required are 11. Okay, 11. So now we will calculate the going length. So after this we will calculate the going length. Going length. So going length is equal to, एक trade कितीचा आहे? Single trade is of 280 mm. So how many trades are required for the single flight? 11 trades are required. So 280 into 11. Do the calculation, you will get the answer. 280 into 11. What is the answer? 3080. 3080 mm. So now this going length, see this answer we have calculated over here, 3080. This is our going length. This is the going length. Now we will move to the previous slides. So here what is our going length? So the going length is from this point here to this point. So this is our going length. This is our going length. Okay, up to these points. So this length we have calculated, and it is 3080 mm, and this we have calculated, it is 3080 mm. This length. So 3080 mm, then I will draw over here number of risers and trades. I will show over here the trades. So now I will draw these lines are like this. You can understand that I am not going to draw the dotted lines for the second flight. Okay, I will not draw the dotted lines for the second flight. I hope you will understand. Okay, so here, and also I am drawing these trades randomly. Okay, I have not calculated we have calculated, but I have not counted that how many trades I have drawn over here. So it should contain the 11 trade. Okay, it should contain the 11 trade. So we will see, this is 1 2 3 4 5 6 7 8 9 10 and 11 trade must be there. One trade is less over here. So now this is 3.08 meter. Now what is the total length? What is the total length? It is 5.8 meter. Okay, this total is 5.8 meter from this point here, from this point to this end point here at this end point. This total distance they have given us as 5.8 meter is the total distance. Now if you subtract this from 5.8, 3 point, if you subtract this 5.8 minus 3.08, it will be 2.72. Okay, it will be 2.72. So I will show over here this total length. This total length is 5.8 meter. This is 5.8 meter. This total length. Okay. So the remaining length is, so what length remains? It is 5.8 minus 3.08, which is equal to 2.72. So this 2.72 length is divided into two, what we can say, two groups. So therefore L is equal to what? We will see L dash now. It is 2.72 divided by 2. So we will get the answer as 1.36. So this remaining length from here to here, uh, this remaining length, this length and this side, this length is 1.36. Okay, this is 1.36 meter. This is also 1.36 meter. Okay, and this length is from this point here to here, it is 3.06. So now this is our total staircase. Now see, when your slab, now if I show you the spanning of the slab, so the slab is spans in this direction. This is the direction of spanning of the slab. Okay, this is the direction of spanning of slab. Slab spans in this direction. समजतंय का? आधी काय होतं, इकडं सपोर्ट होता, इकडं आणि इकडं, त्यामुळे स्लॅबची डायरेक्शन. So first in the previous problem the support was provided over here at this point. Okay, So the spanning will be इकडं support and इकडं support म्हणजे असा झाला span. इथं पण if the support is at this side and support is over here, then it is spanning in this direction. Now support is given at these 2 points. So the spanning of slab is this way. This is the direction of spanning of slab. Okay, this is the direction of spanning of slab. And the spanning direction of the staircase is horizontal. The spanning direction of west slab is horizontal, like this. Okay, but this landing slab is now in vertical spanning. Okay, so now in this case, now we are going to use that g plus x plus y to calculate the effective span. Now to calculate the effective span, okay, to calculate the effective span, if I draw the line over here and I will draw another line over here. So now if I write this is your x, this is also x, this side it is y, this side it is y, and this going length is nothing but it is g. Going length is nothing but it is g. So what is the effective span now? We need to calculate the effective span. Okay, for before effective span we need to calculate the value of x and y. Now here you will see that this total is 1.36 meter, so this total is 2x, so 2x is equal to 1.36 meter, so x will be 1.36 by 2. Similar is the thing with y, so I will write here only. If you see from the diagram, it is clear that 2x is equal to 1.36 meter. So therefore, x is equal to, what will be the value of x? It is 0.68 meter near about. Okay. Similarly, guy, this is the short form of similarly. Similarly, 2y, 2y is equal to also 1.36 meter. So y is again 0.68 meter. So these are the values of x and y. Now we can calculate the effective span. Okay. So to calculate it now, so here now this is our complete diagram. Now we will move to the effective span. So effective span, effective span. So effective span, we can calculate this now. So effective L effective is equal to, it is g plus x plus y. And here in this case you see that x and y are less than 1. X and y are less than 1. Okay. So now therefore L effective is equal to G is 3.08 plus 0.68 plus 0.68, which is equal to, calculate the answer and let me know that, calculate it now. 4.44. Okay, good. 4.44. So 4.44 meter, which is equal to 4440 mm. This is the effective span of the staircase now. This is the effective span of the staircase. Now rest of the procedure is same again. So after this we will calculate the depth. So I will give the heading depth of depth of west slab. So you copy it down. Depth of west slab. So what we will assume? We assume depth is 40 mm per meter span. This is our assumption. Later on we will take the check for depth. Right now we have assumed it. Assume depth is 40 mm per meter span that we have assumed. Now what is our calculation now? Then capital D, that is our overall depth. It is 40 into, what is the span in meter? It is 4.44, which is equal to. Now calculate the depth and let me know the answer. And do the calculation fast. What is that? 40 into 4.44. So 4.44 into 40. What is the answer? 177.6. Okay, so the answer is 177.6 mm. So now this is the depth. We will round up the depth to the higher side. It is 180 mm. So depth is the 180 mm. So now we will take the loads, different types of loads acting on the staircase. So I will write here next heading, loading calculation. Loading calculations. Now we know the depth, we know the span, so we will calculate the loading now. So in the loading, first thing is the dead load. Dead load. Okay. So dead load, we need to calculate the dead load first. We need to calculate the dead load first. So now how to calculate the dead load? Dead load on the slab. So weight of slab. First thing is weight of slab. So now what is the weight of slab? That is overall depth. That is overall depth D. So what is our overall depth? It is 180. So it is 0.18. This is our overall depth into per meter width. Okay, into 25 into. Now west slab is inclined. So I have already told you the factor which we used over here. It is under root what? R square plus T square and whole divided by T. So in the next step you put the values. Here I will write only D. This is the overall depth D. So now again weight of slab is equal to D. What is the value of D now? It is 0.18 into 1 into 25 into, here I will write under root our risers and trade 0.15 square plus 0.28 square. Okay. And it is divided by T 0.28. So let me know the answer. Weight of slab. What is the answer now for weight of the slab? Give the answer in the chat box. 5.1. Okay. So the weight of slab is 5.1 kilonewton per meter. Okay. So after the weight of slab, we will calculate weight of steps. Next thing is weight of steps. Weight of steps. Instead of this, I will directly take here weight of steps is equal to. So weight of steps, how do we calculate the weight of steps? So you know the formula for weight of steps. It is R by 2 into 25, or 1 half R into 25. Half R into 25. This is the formula for weight of steps. So half into R. R is our riser. So it is 0.15 into 25. So let me know the answer for weight of steps. What is the answer? 1.875 is 1.875 kilonewton per meter. So this is the weight of step. Now next thing is floor finish. Okay. So floor finish, this also comes into the dead load, which is equal to 1 into 1, which is nothing but 1 kilonewton per meter. So after the floor finish now, we will go to the live load. Okay. So after the dead load, next thing is the live load. Live load. What is live load now? It is given in the numerical 3 kilonewton per meter square. So 3 into 1, 3 kilonewton per meter. So now the next thing is that total load. Okay. So here kilonewton per meter square. And next thing is total load. So I will write over here total load. So total load is total dead load plus live load. Okay. So what is the total load now? Add all the things and let me know the value of total load. So 5.1 plus 1.875, 5.1 plus 1.875 plus 1. This is total dead load. Okay. In that, if you add the live load, that is also okay. If you add it separately, that is also okay. There is no problem. So plus 3. Live load also we have added over here. So now let me know the answer. 5 plus 1.875 plus it is 10.998. Okay, so it is 10.98 kilonewton per meter. So now calculate factored load. Okay, so the factored load. Next thing is factored load. So multiply this load by 1.5. 10.98. So the answer is 16.46. Okay. Answer is 16.46 kilonewton per meter. This is the factored load. Okay. So now after the calculation of this, these are the loads which are coming on the west slab. Okay. So हे सगळे loads कुठे act होणार आहेत west slab वरती. Similarly, we need to find out the loads on the landing also, landing slab. Okay. So here load on landing slab. Load on landing slabs. Okay. So the loads on landing slab. So first load is that weight of slab. First, we will take into the account weight of landing slab. Weight of landing slab, it is equal to, what is the depth? Overall depth is, what is the overall depth we have taken? I think 180. Okay, so it is 0.18. You know that into 1 is there, and into 25. So if you solve, you will get the answer. What is the weight on slab? Weight of landing slab. How much it is? 4.5. 4.5 kilonewton per meter. Then take the floor finish. So weight of floor finish. Weight of floor finish, or you can directly write over here floor finish. So what it is, 1 into 1, which is equal to 1 kilonewton per meter, and then live load. Live load is equal to 3 into 1, which is equal to 3 kilonewton per meter. Now calculate the total load. Okay. Now calculate the total load and let me know the total load. So what is the total load now? Total load is equal to, what are the values? 4.5 plus 1 plus 3. 4.5 plus 1 plus 3, which is equal to 8.5. After that, calculate factored load. 8.5 kilonewton per meter. Then factored load or ultimate load. This is also called as ultimate load. So 8.5 into 1.5. What is the answer? 12.75. Good. So 12.75 kilonewton per meter. Now I will draw the line diagram to calculate the bending moment. Same concept is there, which is explained in earlier numerical. So here, this is the total span. Now the supports are provided. So now I will draw the diagram over here. Now the supports are provided. These are the supports. And now I will plot the going length. Going length will be at the center. So what is our going length now? If you see, going length, what we have calculated, this going length is equal to 3.08 meter. Now if I consider the center point, then what is the value? 3.08 by 2. So 3.08 divided by 2, it works out to be 1.54. So from the center 1.54 to right hand side, from the center 1.54 to left hand side. That I will mark first. So here 1.54, that is from this point to this. Okay. This total length, it is 3.08 meter up to these points. Okay. And now if you know that from here up to the wall end distance is 1.36. Okay, let us assume that this distance is a. This distance is A, and width of support it is given as 230 mm. So this A will be, what is the value of A? It is 1.36 plus it is 0.23 by 2. So its value will be, what is the value? 1.36 plus 0.23 by 2. What is the answer? 1.475. Okay, so we will take it as 1.48. And same, if we consider this distance as B, same thing is there. A is equal to B. Okay, A is equal to B. So I will write over here. I will write these values. So these are 1.48 meter. This is also 1.48 meter. Okay. And now load is also acting on the staircase. Okay. So I think it was mute. I will explain it once again. See what I have done. We know the going length. Going length is 3.08 meter. We have already calculated. I have picked the center point. From the center point to the right hand side 1.54, to the left hand side 1.54. So this total will become 3.08. Now the remaining length. This length we need to calculate. Okay. So you know that from this point up to the outer side of the wall it is 1.36. It is 1.36 that already we have calculated, but width of support, this support width is 230 mm. So up to the center of support if we want to calculate, then it will be 1.36 plus 0.23 by 2. So it will become 1.48 meter, and the same thing is repeated to this side also. Okay, and same thing is repeated to this side also. Now we will give loading. Now the loading here it is like this, and then the loading up to the remaining part. This is the loading on the remaining part. Landing. So this is the landing, and this in between is the going length. So west slab load is always exerted on the going length. So now what was the load we have calculated for west slab? For west slab, what was the load for west slab? इथे किती लोड कॅल्क्युलेट केला होता ते सांगा. आणि हे लँडिंग वरती किती लोड आला होता ते सांगा. फॅक्टर्ड लोड, दोन्हीचे फॅक्टर्ड लोड सांगा. लेट मी नो द व्हॅल्यूज. I think this is 10.98 something. Please check the values. And what was the load over here? Fast. मी सांगितलं नाही तर कसं होणार ते. I don't know the values. And as it is getting disconnected, it is not there on the previous slides also. So let me know the value. What was the load on this length? 16.46 and 12.75. Okay, so good. 16.46, 16.46, and then 12.75. 12.75 kilonewton per meter. So this is the loading. This is also the same load. 12.75 kilonewton per meter. Now we need to solve this. So we will take the different points over here. This is our point A. This point is B. here it is point C, point D, and at the center over here, at center, here is the point E. So we want to calculate the maximum bending moment. Now if you see, this beam is symmetric. Now this will become symmetric in terms of loading, in terms of geometry, and in terms of support also. So whatever the maximum bending moment is there, it will be at the center of the beam, at the center. So now to calculate the bending moment, first of all we need to calculate the reactions RA and RB. Either I should calculate RA or either I should calculate RB. So first of all we will do the reaction calculations. So we will take the moment of all the forces about B equal to 0. So taking summation m moment of all the forces about B is equal to 0. Clockwise is positive, anti-clockwise is negative. Okay, so from point B we need to measure the distance of this reaction RA. So from point B, RA is at a distance of how much it is? I think 5.8. Am I right? 3.08 plus 1.48 plus 1.48. It is 6.04. Okay, so it is RA into 6.04. Then this UDL, convert this UDL into the point load, and it is moving downward. So this is moving upward, so this will rotate in clockwise direction. If you see the direction about the rotation, this will rotate in clockwise direction, and this UDL, it will rotate in anti-clockwise direction. So it is minus 12.75 into 1.48. Now what is the distance of this force? Now this UDL is get converted into the point load. And now see the distance. What is the distance from point B? That is the important thing. Okay. This UDL will act somewhere over here. Okay. This UDL will act somewhere over here. If this is converted into the point load, then it will act somewhere here. Okay, at the center of this. So what is the magnitude of this force? It is 12.75 into 1.48. This is the magnitude. And what is the distance? Now if you see the distance, this is the distance, this much. So it will be 1.48 divided by 2. So this distance will be 1.48 divided by 2 means 0.76, I think so. It is 0.74. So this is 0. So this distance is 0.74 meter. Okay. Similarly, every time you need to convert the UDL into the point load like this, and then take the moment of the force. So here the next point is, now calculate the distance. It is 1.48 plus 3.08 plus 0.74. What is the value? What is the value? We want to calculate the value. 5.3. Okay. As per my calculation, value is 5.3. Is it right? Value is right. So we will take the next term now. Again minus. Now next this UDL, it is 16.64 into its span is 3.08. So what is the distance? Now if this is converted into the UDL, okay, this is record, then this will act here, somewhere here, this point. Okay, and now what is the distance? What is the distance? It is from this distance we need to calculate. It is 1.54. 3.02. Okay. So this is 1.54. So the total is 1.54 plus 1.48. So it will become 3.02. Okay. Again minus, it is 12.75 into 1.48 into, now if this converted into the point load, this UDL will act somewhere here. Okay, this UDL will act somewhere here. Okay, so this distance will be 0.74. 0.74. Okay, and now this RB is passing through point B, its moment is 0, so all this is equal to 0. Therefore RA is equal to, let me know the value of RA now. Do the calculation for RA and let me know the value. What is the value of RA? Drop the answer into the chat box. 44.23. So the answer is 44.23 kilonewton, and it is positive answer, so it is moving up. Okay, so as we know now, the maximum bending moment will be there at point E. The maximum bending moment is at point E. So we will take the section at point E and consider the left hand side equilibrium. So bending moment at point E. So for the bending moment at point E, take section at point E and consider left hand side equilibrium. Consider left hand side equilibrium. Therefore, bending moment at point E is equal to, what is the bending moment? So now if you consider the bending moment at point E, this reaction RA is there. Okay, point E is somewhere here. So the distance of RA from point E, this total distance, how much it is? If this is 1.54, this the up to this point is 1.54 plus 1.48, means it is 3.02, and RA is moving up, so it is positive. Okay, it is positive. So it is RA. The value of RA was 44.23. So it is 44.23 into 3.02. Okay, 3.02. Then next is the here at E now. If you see, this is the UDL 12.75, which is acting on the span 1.48, and this half UDL which is acting on the span of 0.74 for 16.46. For these two also we need to calculate the moments. Both these are moving downwards, so both these values are negative. So here it is 12.74 into 1.48. So minus 12.75 into 1.48. Now this UDL gets converted into the point load. And what is the distance? The distance from point E is, it is 0.74 plus 1.54. Okay, so 1.54 plus 0.74. It is 2.28. I think the distance is 2.28. Again minus, the third thing is that this UDL 16.46. Okay, 16.46. Length is DE. The length of UDL is DE, and which is 1.54, and this will act at the center of this. So from point E, it is at a distance of 1.54 divided by 2. So 16.46 into 1.54 into 1.54 divided by 2. Now if you solve this, you will get the bending moment at point E. Let me know the answer. It is 71 point something or what? 71.03. Okay, so it is 71.03 kilonewton meter. So this is your maximum bending moment. This is the maximum bending moment. Now after the calculation of bending moment, we will take the check for depth. So check for depth. Check for depth. How to calculate the check for depth? It is what we will do. Equate equate maximum bending moment to moment of resistance. So the maximum bending moment is, what is the maximum bending moment? It is 71.03 into 10 raised to 6, which is equal to न्यूटन mm मध्ये घेतलेले आहे 0.138 fck b d square. Okay, b d square it is bd square. So now if you put the values, then 71.03 into 10 raised to 6, which is equal to 0.138 into fck is 20 into b is 1000 into d square. D required depth square. Therefore d required is equal to, what is the d required? Answer is 160.42. It is 160.42. And d provided. So effective depth, if we have not calculated, then here I can write capital D, it is 180 mm. So if I assume clear cover is equal to 15 mm and bar diameter is equal to 10 mm, then small d is equal to what? 180 minus 15 minus 10 by 2, which is equal to how much it is? 160. Okay, so both the values are near about same, 160 mm. So this is a very optimistic design. 160 mm. So now what we will do, we will keep the depth as it is almost equal. Okay, or otherwise you can go for increase in 10 mm. So if you increase the depth by 10 mm, that is the your effective depth, then your overall depth also get increased, and you have to redo the calculation of load. So I will write here, hence provide capital D is equal to 180 mm and small d is equal to 160 mm. Okay. So now calculate the AST, area of steel. Area of steel, that is AST. So what is the formula for area of steel now? AST is equal to 0.5 FCK BD divided by Fy in bracket 1 minus under root 1 minus 4.6 mu upon FCKBD square. Now put the value and you will get the answer. And let me know the answer of this. So put all the values. FCK is 20, B is 1000, D is 160, Fy is 415, Mu is 71.03 into 10 raised to 6. So put all these values in this formula, that is in this equation, and let me know the value of AST in mm square. So what is the answer then? 1536.26. Okay, 1536.26 mm square. This is the correct answer. Okay, so instead of 10 mm now this area is big. Go for 16 mm bar diameter. So provide 16 mm bars, diameter bar. Okay, so we will calculate first the number of bars. Number of bars is equal to 1536.26 divided by 16. So how many number of bars are there? So 1536.26 divided by 16. So you will get the number of bars 7.64. So we cannot provide 7.64 numbers, so we will round it up to 8 numbers. So 8 number of bars, and each bar is having diameter of 16 mm. So calculate the area of steel provided. What area of steel we are going to provide over there? So area of steel provided, it is, we are going to provide 8 bars and each bar is having the diameter of 16 mm. So pi by 4 into 16 square. Now this is your AST provided. 1608.4 mm square. Okay, so it is enough now. Today we will stop over here.